So I am going to talk about something both very topical and also get very technical at certain parts. So hopefully, this is the for practitioners session. Everybody brought their coffee. Isn't that cool how he does pictures of, this is going to be my new profile picture, is the coffee. All right, so obviously fake news has been in the news, has been very popular topic of conversation and a very important growing concern for democracy and truth for the past roughly 2.5 years, strangely enough. We first started thinking about this about 2 years ago when natural language processing, natural language understanding, it didn't get its biggest kick in 2016, but starting around 2016, 2017, the ability to work with text in ways that we had not dreamed would be possible, at least not this decade, really started to take shape. Last year, 2018, was, aside from maybe the breakthroughs that we had in 2013, the biggest year in natural language processing, and something that, because we were actively working on this project at the time, has been very, very exciting for us and has really helped in improving the ways that we approach working on this project. So a little bit about just a quick overview of our agenda. I'm going to start by just framing what is the fake news problem, at least what is the kind of fake news problem that we're trying to solve. And then I'm going to move very quickly through no-context embedding. So this would be pre-2018 techniques for using natural language understanding. And then we'll spend most of the time doing a little bit of a technical review of transformers and how they have added to our capabilities as natural language understanding deep learning applications. And then we'll, hopefully, if I can talk really quickly and speed through all the important stuff so you don't ask too many questions about the technical stuff, we can do some demos, and you can yell out your favorite fake news websites, and we can check them with the app. OK, so part one, what is the fake news problem? There are a lot of different ways you can approach the fake news problem. The way I like to phrase what we're doing is it's one of the chopsticks in a bundle, so to speak. It's easy to break a single chopstick, but a bundle of chopsticks is very difficult to break. This is one approach. It's not the end-all, be-all approach. What is an approach that doesn't work and that is hard to scale? Solving the truth problem. Solving fake news problem construed as detecting the truth, extracting the truth from the text, or the claims at the truth from the text, and then comparing it to a database that has all the true factoids in the world is very hard. It's very hard even if we're not talking about new things that may not be in your database of all the true things in the world. But even if you did have those that were refreshed instantaneously because I don't know why you have some sort of God algorithm that's spying all over with Internet of Things, you still, it's a very challenging problem technically to extract factoids, check inferences, and see if what is actually being claimed in an article has this correspondence with the world. So what we decided to do was not approach it from a fact-checking point of view. Fact-checking is important. It's a valuable contribution to society, going out, doing that hard work, figuring out what the world is like, and then seeing if what's written corresponds to that. It's very difficult to do with algorithms. And that's not to say there's some pretty amazing advances in inference detection and things like that in natural language understanding. That's just not what we're doing, because while they're amazing advances, we need to be sober about this. We're talking at best in some of the easiest cases, 80% F1s. So the way we decided to approach the problem really centers around this psychological phenomenon, that increased emotional content tends to negatively impact your cognitive functions. It makes you less able to reason about what you are reading when you care about it, when you are angry, when you are upset, when you when you're in a rush. if you are emotionally engaged with what you're reading, you are not thinking about what you're reading. And so there's sort of like this, you can create this for the MBAs in the room. This is one of those like 4-quadrant charts. There's on one dimension, there's what's true and what's false. And then on the other dimension, there's something that's maybe a little bit more about the presentation. Is the presentation something that's aimed at credible information sharing, aimed at putting something in a format where you can use your best rational self to read and evaluate what's being presented? Or is it presented in a way that is kind of designed to turn off, whether by intention or just because the person who is writing it is very good at and has learned, maybe through practice, how to get you to rationally evaluate what they're saying less by emotionally engaging you more. So you can think about these 4 quadrants kind of this way. You got the good journalism, that's the good. It's saying it's sharing the information in an incredible way, and it's happens to be saying the truth. Accidental falsity, so this would be cases where a true blue journalist who has the best intentions just gets things wrong and should be very responsive to making a retraction if it turns out that there is evidence to the contrary. There's incidental truth, so the bad guy fake news people, they might accidentally say a couple things that are true. That would count as the orange. And then there's the malicious fake news. So this is maliciously trying to promote a claim or claims that are indeed not true. And so while you can be in any of these 4 quadrants, one of the hypotheses is that if we can detect in the y-axis, the up-down axis, then we'll be able to detect, because of a correlation, the left-right axis. Now, this is not guaranteed, but the reasoning is that somebody who has the truth on their side doesn't need to distract you with emotional obfuscation. So this is the scalable problem that we are trying to solve with machine learning, with natural language understanding, trying to detect when something looks like it's credible information sharing versus emotional manipulation. End of the philosophy part of the talk. Now let's do a quick review, just a show of hands. Who works with natural language processing, is familiar with word-to-vec and embeddings in general? Most of the room? OK. So this is the word-to-vec algorithm. I'm not going to go into detail on what it does, but it's the whole idea for those 30% of you in the room is it took us out of the dark ages, that is to say 2012, of natural language processing, where we would do one-hot encoding of words, vectorize them as these way too many dimensions, tens, hundreds of thousands, even millions of dimensions to represent our vocabulary, and allowed us to semantically embed these words in sufficiently dense representations in vector spaces, usually 200 to 300 dimensions, where there is the semantics are captured in the way they're embedding. So 2 words that are synonyms might be placed close together in the vector space, and there are different geometric relationships. So there's a plurality direction. You can do the famous, maybe too oft quoted, king minus man plus woman equals queen vector. And you can start to do this arithmetic that matches our conceptual relationships to do like analogy completion. So 2 other popular no-context embedding options, and these are not all of them, just the top ones. So we have the original word-to-vec, then glove, and so if you came out of Stanford, you probably roll with glove a little bit more because that's what the Stanford people did. And then there's fast text. That does not necessarily solve all the problems, though. You might think about this sentence, which really, the meaning of the word bank in this sentence really has a lot of dependency on the rest of the words in the sentence. If we fill in the man crossed the river to get to the bank, that is a bit different than the man crossed the street to get to the bank. Or maybe just how you interpret words in the context of the sentence matter, right? The man saw the dog, or the reference of the words, right? This is sort of like a parsing issue. The man saw the dog with a telescope. What was the dog doing with the telescope? The dog wasn't doing anything with the telescope. The man saw the dog with the telescope, but how do you tell? How do you tell the difference? So one way of managing this issue is you start to move into semi-context-rich applications using recurrent neural nets. LSTMs in particular are very good, same with GRUs. So these manage things like references and relative clauses and grammar and all of those pieces that in a sentence that we naturally keep track of even when the speaker is doing a very, very long run-on sentence. So you can stack those LSTMs, you can stack RNNs in general, and you can get multiple layers of context extraction through hidden layers. You usually want to do it in a bidirectional LSTM. So you'll look at it forward and then backwards, and then you'll get a pivot point around each word that gets kind of the context from both directions. You'll also look at the one that's all the way front to back and all the way back to front. So like this one that's diagrammed here, and that'll give you the full context of the sentence. Attention. So this is getting us to around 2016, 2017. Using attention is very helpful. So this is, you're not just looking at that full context, so one front to back and back to front vector. You're also looking at the pivot representations of the words as they go through the RNN. And that allows you to pay attention to, for each word, what's the most important part of this word? What kind of encoding of the text that we're looking at should we pay extra attention to? Should we maybe propagate forward in the signal that we're sending to the next layer of the algorithm in order to highlight what was important about that? Is that enough context for these? Turns out, at least in our experiments, you can do even better than just using these techniques. So 2018, so transformers, attention is all you need as actually the end of 2017, and it was a NIPS paper, which meant that NIPS applications are due in like 2 days. So it was early 2017 when they wrote the paper, but it didn't really get adopted until, or didn't get released to the public. The public didn't really consume attention is all you need until really the end of 2017. So I'm going to round it to 2018. Everything else happened last year. All of these advances, and we're still seeing. Microsoft just came out with a descendant of BERT that is supposedly even better than on a lot of the benchmarks. So, what are these algorithms? The first one that's in the RNN vein, or the only one that's in the RNN vein, is ELMo. So what ELMo does is it uses the same diagram, although, and a disclaimer, all of the diagrams I use from now on, I steal from illustrated BERT and illustrated ELMo, JALAMMER at GitHub. Amazing diagrams. You can't do better, so I just stole them all. There's the link. So this is the same one as this, only with cute ELMo pictures. And what ELMo does is it does this multi-layer embedding, and then it embeds relative to the context of the sentence. So one layer might get the sort of like per sentence embedding, but the second layer will capture something else about the grammar, and the third layer will capture something else about the word in context in the grammar. And it gets you, when you have these 3 outputs from each of the layers, looking at all of them and feeding those all in sometimes as signal to upstream neural net will give you better picture of what's going on in your sentence when you're looking at the individual words in the context of the rest of the sentence. ULM fit. So this is the Jeremy Howard camp and the fast AI. So the big thing about ULM fit was you actually can do, even if it's a dense network, what you can do is you can capture multiple layers, word to vec, glove, fast text. What they're doing is not deep learning at all. It's actually pretty shallow. It's one layer of embedding. These universal language models do multiple layers of embedding, so you're abstracting not just the individual terms, but also what their position is in the context of the entire vocabulary, in the context of the grammar, and you can start just like we see with computer vision and with convolutional neural nets. You start to get these high-level abstractions of what it is that you're actually feeding in with the raw data, and it allows you to have a much better encoding of your text. Now, just like with computer vision and with CNNs, and this is the important contribution that Howard and team made, is fine-tuning matters. The way you fine-tune matters, and so you only really want to do a lot of changes to that top level of the language model. And so you do this gradual freezing or defreezing as you're training of the top level, and then less and less of the lower levels. And that's really that's what's depicted here. But 2018 was the year of the transformer, and so with 12 minutes left, I'm going to talk about transformers a bunch, and then we're going to do some demos. So what is a transformer? That's the diagram from the original paper. It seemed pretty opaque the first time you see it. You have the only thing you might want to take from the picture on the right is that there is sort of an input and an output side to it. This GIF is a little bit more or less intimidating, but what are those? You know, it's like a video game. What does that really mean that's going on right there? So let's break it down. You have an encoder side and a decoder side in a transformers. And the right way to think about it when you're trying to get your arms around what this algorithm is doing is you think about it as like a translation, a neural machine translation paper or task. So you have your, I don't know the French, that translates to I am a student. You feed it into the encoder, and then the decoder is going to decode that into whatever language you want. So inside that encoder and decoder boxes, what you have is two kinds of main block, right? You have a self-attention, and don't worry about what that self-attention is. I'm going to go into detail on that in a moment. And then you just have a feed-forward layer. So it's just a dense layer, and there's there's a residual highway, but it's effectively just these two components. And then in the decoder side, it's also just that component, but it has that middle encoder-decoder attention, which is actually the same as the self-attention. It's just taking information from the encoder side. So what's going on in that encoder? So you have let's reduce our sentence to just this thinking machines. We want to encode the thinking machines as some sort of vector representations. So you have a self-attention mechanism. So this is a multi-headed attention mechanism. It's a bunch of attention mechanisms, like I was talking about earlier, where it pays attention to every word in context. That feeds into, that gives an output for each representation, so an attention representation. So this is an encoding of the words in context with all the other words. Then there's a layer normalization. You'll see this residual highway on the side. It goes to your neural net or your regular dense network, a feed-forward network, and then you can repeat that over and over and over again as many times as you want. So these transformer encoder and decoders have several layers of these self-attention followed by feed-forward, self-attention followed by feed-forward encoder blocks, and then they also have the same thing on the decoder side. What is multi-headed attention? Multi-headed attention is just attention mechanisms, but lots of them all together. The way to think about multi-headed attention is in terms of this key, value, and query triplets. So you have a query, you have a key, and you have a value that goes with that key. And the way you get your output for each attention head of the multi-headed attention is you take the key and the query and the key. You do this dot product. They did a clever thing just to manage dimensionality growth, much like when you initialize. There's the GLOT. When you divide by the size of the matrix when you're initializing your neural net parameters, you do the same thing. You divide by the square root of the dimension of the k dimension. So you do that m times to get your multi-heads. Then you get all of your z outputs from each of these heads, and you do one more set of parameters that compresses all of those heads. So in this case, we have 8, because we all code in Python, so we start counting with 0. So 0 to 7, that's 8. And we multiply this W0 matrix. You get a single embedding for all of those different multi-headed attention outputs. And you have one Z embedding for each term. So if you think about the way you have thinking is this top row, machines is this bottom row, and then you get also top row, bottom row Z. So 2 words in, 2 words out, or 2 embeddings out. And same thing with if you have M words. One thing I skipped. The way you input it, you don't input it necessarily as one hot encoding. You can input it as one of these more shallow word embeddings. So you can do a word to vec or a glove embedding of your individual terms to kind of bootstrap doing this multi-headed embedding in context. All right, so you have several encoder layers. You have then decoder layers. The only difference with the decoder is that you have the embedding of the decoder come in. Before, when I was talking about the encoders, the key, the value, and the query is all the same word. That's why it's self-attention. In the second component of the decoder, what's bringing in is not the key, the value, and the query are all the words. We do that for the first layer, but for the second layer, we have the key, the key K actually coming from the encoder. Same with the values. So those are coming from the encoder, and that's how you bridge the encoder to the decoder in order to get that transference from encoder side to the decoder side. And then slowly but surely, I'm not going to let the GIF go through because we only have 7 minutes, but this is how it goes through the neural machine translation. Late 2018, but not late enough 2018, like around November, GPT-1 came out. So GPT-1 essentially took this attention is all you need transformations or transformers and said, okay, I'm going to look at the decoders. What the decoders do is they take the words so far, and then they kind of predict the next word, right? Well, we could do that. We can do sentence completion with this, and we can actually train the decoders, and you just have one full stack of decoders to, you mask the next word, so you mask the word on the right, and then you predict it, and then you keep on going through that. GPT-1 broke all the records. Bummer that they didn't publish like at least 6 months earlier, because like a month later, BERT got published. So the Google guys got scooped by the Open AI guys and ladies. BERT does the same thing, but it does it on the encoder side. So on the encoder side, the GPT-1, the Open AI team, wanted to do it on the decoder side because it seemed very intuitive. We have this missing word. We want to fill it in. Done. Encoder side, what are you going to mask? What are you actually training as a task in order to learn how to embed these words? Well, the BERT algorithm does some things very clever. It masks words inside of those, the input sentence. So it randomly masks them, and then it also it does random masks, and some of them it randomly replaces. And by doing that in the carefully tuned balance, you can actually just have it fill in the blanks that have been randomly masked and train the BERT algorithm, the encoder side only, in order to reconstruct and encode whatever your text is. So they did a base, presumably because it was curiously the same size as the GPT-1 size, and that's what the BERT base one. They also did a large one to flex the Google muscles of having all the GCP resources in the world. And here's what's cool about BERT. You can use it for several different kinds of tasks. So yes, you can use it for encoding, and there's BERT pre-trains out there that are very useful. You can use it for question answers. You can use it so you have like 2 sentences. You can do it for implication. Here's the question answer. Here's the classification pair, so implication or consistency or non-relation. They also have this CLF token or C token here, which is this kind of like general context of a whole sentence token that encodes everything about the sentence. And that's useful for classification. So you can take that CLF for classifier, feed that text or that encoding of the entire text into a classifier, and then answer, give your classification question of choice about the text. So something like semantics, or sorry, not semantics, something along the lines of sentiment analysis, or Is this credible information sharing or emotional manipulation? Right? That's the classification task you can ask. One more thing. So in 2019, the recurrence is back. Don't think that all those years we spent with recurrent neural networks are out the window. Getting these long-term relationships intra-text. Transformer XL is a approach to allowing us to go through with that transformer approach, which is a sequence-to-sequence approach, but doing it in a sort of recurrent way so we can look at long spans of text. Okay, so back to fake news. We're good. Okay, so our job is to detect if something is emotionally manipulative, and so we came up with six classes: journalism, wiki, opinion, satire, sensational, and agenda-driven. And we trained it independently on each one of those. The backbone is still this hierarchical structure with the attention mechanisms and with sequence-to-sequence components. But now we have the opportunity, anywhere we see a sequence-to-sequence and anywhere we see an embedding, we can use in-context embeddings like BERT and ELMo and kind of like kick away the ladder, replace with these new kinds of embeddings and see what comes out. And just to make that a little bit less opaque, I know I'm talking very fast. So with the recurrent neural networks, you have for each word, you have an output for the bidirectional LSTM. You have that same output with say, a BERT model, right? You have each word, you get an output. But you also have a full context of the entire sentence output, like the CLF output. So you can feed that in for the full end-to-end. So everything that you might want to do with a bidirectional LSTM, you can also do with a transformer. So I have benchmarks for two of these. We have some other results for the other ones but you see similar patterns. I just haven't finalized that we have our best numbers yet. If you see with the naked BERT and ELMo model, so this is where we don't use any of the other infrastructures. We just pull out like a transformer or an ELMo. Unfortunately, that doesn't really beat baseline yet. But if you do this interweaving of hierarchical methods with replacing recurrent neural networks with either BERT or you replace different embeddings with ELMo, you do start to see big improvements. So both BERT and ELMo configs have configs that can add about 1% recall with comparable precision, which is when you're getting to these high, it's sort of like Zeno's paradox. As you get closer and closer to 100%, it gets a lot harder. So 50 bips is great, 100 bips is even better. And ELMo can also be used to get much higher precision. For hate speech, so this is one that's not live, mostly because we don't want to tell people they're hateful unless we're really, really sure. We also get a lot of some big bumps, and in particular, I was encouraged by these two BERT and ELMo ones because hate speech is a situation where you need to have very, very high precision. You need to be very careful that even 2 out of 100 people that you say are racists. Wrongly accuse a racist, even if you get a 98 out of 100 correct. That's a very hard bar. Not as hard as bar of self-driving, but it's something that you want to make sure that you get right most of the time. Okay, that's now it's fun time for questions and for demos. I want to talk about one more point about this context of how you approach the fake news problem. So my former colleague, Gary Marcus, the founder of Geometric Intelligence that was bought by Uber, wrote this op-ed last year, bummer Zuckerberg, no, AI won't solve the fake news problem. And he goes into a lot of great detail about why this article, Boy Scouts have decided to accept people who identify as gay and lesbian among their ranks, and girls are welcome now too. This is not Gary Marcus, by the way. This is World News Daily, which is like the InfoWars guy, into the iconic organization, which has renamed itself Scouts BSA. So what's next? A mandate that condoms be made available to all participants of its global gathering? Marcus, was this account true or false? Investigators at the fact-checking site Snopes determined the report was mostly false, but determining how it went afoul is a subtle business beyond the dreams of even the best current AI. So In the problem that they're trying to solve, automating fact-checking, yeah, probably right. But if you look at it in a different way, if you look at it in the way that we have been approaching it, you actually, it seems to be very easy to detect that this is highly sensational and highly opinion text. So something to be suspect, to find suspect. Not only that, remember we have the attention mechanisms embedded throughout the algorithm, so we can pull out the attention mechanisms at the what are the most important sentences in this paragraph level and identify that actually 3 out of the 4 quoted sentences in that paragraph that I just read from World News Daily, Walt the we named it Walt after Walter Cronkite. The algorithm pulls them out and says that that's why we think it's sensational and opinionated. Rolling Stones, the original Fear and Loathing algorithm got satire and agenda-driven. And then one time somebody called out, oh yeah, but what if it really is a big deal, like the Kennedy assassination? And so evidently it gets the Kennedy assassination right too. OK, so thank you. We've got 0 seconds, but I'm sure the conference organizers will let us do a little bit of demoing if people want to yell out their favorite websites.